All right, everyone. Well, good morning. Welcome to your second lecture. We would normally have a moderator here. I think she might be running a little bit late. Let me just make sure that we have people online. Oh, actually, I'll do it on here. No, I won't. Sorry guys, I think we might be having some technical difficulties. I can't see that we have anyone online yet. do a last minute switch to YouTube. Do you know how to set that up? Yeah, it seems to be. It just says no content. Have you seen that before? Hi Victor, it's Alex here. I'm in the physics theatre, and we don't seem to have any echo feed. So we're supposed to be live streaming. Yes. Oh, really? Is there anything? Is there any way that we can change that right now? Okay. All right, not a problem. All right, thank you. Okay, thanks. OBS. Sorry, can you get onto Teams and ask someone to Teams? Oh, actually, don't worry. Okay. Sorry? Yeah, I think we have to. I'm now tempted to just stream on YouTube because set it up.
Hopefully YouTube.
Yep. We are being recorded though.
By a good.
Yep.
So it should be fine.
Oh, we're 10 minutes in. I'll have to apologise.
I think it'll be fine. It's only the second lecture.
Sorry?
It's only lecture 2.
Yeah.
Did Monday's one go?
Apart from Moodle not being set up. I can't email students now. Abraham's always on night shift, isn't he?
Probably best to send an email after. Well, a lot of people will watch the lecture after it's done.
Yeah. This is going to this. No, I'll leave that open. Okay, everyone. Everyone? All right, sorry for the delay. So we're having some technical issues with Moodle still, so we're not being live streamed today, but we are being recorded, so be on your best behavior. But yeah, so unfortunately no live stream today. And again, apologies for the delay, but welcome to your second lecture. Sorry for the false start. It's not how you start though, it's how you end, right? All right, so before I start, so I've been asked to mention this resource page for COMP1521 students. So one of the students had emailed in at the end of their degree and they went, wow, I just found this resource and that would have been really useful at the start of my degree. So yeah, if you're in COMP1521, so the issue is with COMP1521, you generally need a more powerful laptop, a more powerful machine, more so towards the end of the degree. But yes, so have a look at this resource and yeah, provides tips for purchasing personal computers, how to structure your degree and which electives to take. So C revision and recursion labs. So we are aiming to schedule those week 2, but we still don't have a time set for those. So just trying to make up for lost time, so glossing over things. But in today's lecture, we're going to do a quick recap of lecture 1. So we ended up starting using MIPS web. I hope I gave you enough to get you started so you could have a little play with that, but if you didn't, that's fine as well. We'll go over that again today. Oh. Thank you for that. Yes, so we're going to be going over the MIPS again, then we're going to be talking about system calls in MIPS, style when you're programming in assembly. We're going to be talking about simplified C and using the go-to statement, and we'll get into MIPS control statements. So in assembly, how do we do an if, or how do we do a for or a while? Okay, so recap of lecture 1. So we explored different types of storage and memory. We explored, we looked at loading, how programs are loaded into RAM for execution, the different program segments. So code, data, the heap, and the stack. Okay, machine instructions. So remember, with each CPU, we have a unique instruction set architecture that's unique for the CPU. So the CPU has been designed in a certain way, and the machine code that's designed for that CPU to execute is going to depend on how that CPU was designed. So in turn, we also have we have different assembly languages, because those assembly languages map to the machine code. And so these are called the instruction set architecture of the CPU, the type of instructions that the CPUs will execute. And then, yes, we finished off, had our first look at assembly language in MIPS, and MIPS emulation using MIPSy Web. So one thing I wanted to mention quickly before we get into back into MIPSy is hexadecimal notation. So who has seen hex before? Oh, excellent, good number of people. So I'll just run over this real briefly then. So for hexadecimal, we're still representing numbers, but it is base 16. So the decimal numbers, so I have a table here of how the decimal numbers will map to the hexadecimal numbers. So you can see for 0 to 9, the number representation is the same, but for hexadecimal, we have the numbers 10 to 15 as well. But we run out of numbers in our alphabet. So we start using letters instead to represent these numbers. So 10 represented by A, 11 represented by B, etc., etc., etc. So we will be looking at this more in depth later in this course, though. Okay, so we often use hexadecimal to represent addresses and other binary data, like instructions. So why? So it's easier for humans to read than binary. So sometimes we want to know what the binary values are, okay? And hexadecimal is a lot easier to read than binary. So for each hex digit, that'll represent exactly 4 bits, okay? And 8 hex digits represent a 32-bit value, okay? So it maps really nicely to binary. It's much better than decimal. So if I wanted to know if something was aligned to an integer value, which is 32 bits, I could just look at the hexadecimal number here and go, okay, 0 is definitely going to be aligned. Then I need to add 4. So the next number would be 4, then it would be 8, and then it would be C, and then it would be back to 0 again. No, it would be... Wow, what happened? Why have I got 16 in here? Sorry, I'll have to fix that up and publish again. So we only go up to F here. Okay, so we have so we have 0, 4, 8, C, then we go back to 0. If we were using decimal, we would have 4, 8, C, 4, 8, and now we're looking at the number 12. So then we have 2 as that last digit, and then we have 16, so we have 6 as that last digit. So it becomes a lot more complicated to see if something is a multiple of 4 and if something is aligned to a number of 4. All right, let's move on. So disclaimer, so the code that I write in lectures may not necessarily have the best style. So I'm up here under pressure with all the people watching me, and I'm trying to get stuff done as quickly as possible so that I'm not wasting your time. So for like a concrete guide of how to structure your C code or your assembly code, We have guides on the course website. Oh. I don't have the course website open. Okay, see style guide over here and the assembly style guide here. Okay, so please refer to those when you're looking for good examples of style and not the code that I'm writing. Oh, in fact, I might just highlight that this might be some good reading as well. Because not only do we have the rule for how to style your code, we also have explanations for why we have this rule. Okay, so besides those style guides, you can ask your tutors and look at solutions, lab solutions, and assignment resources as well. Okay, so back to MIPS. So where we left off on Monday, we were writing a simple MIPS program. So we're loading two numbers into two registers called T0 and T1, and then we were multiplying those together. So we're going to be doing quite a bit of MIPS in this lecture. So if possible, I'll get you to bring out your laptops and open up MIPS web, and we can start practicing some coding. Okay, does everyone know how to get to MIPS web? Everyone found it, or does anyone need help getting to MIPS web? I guess the link's at the top of my browser there. Then we want to mul, and I think I got this wrong last time again. T2. T0, T1. Okay, so you might have noticed that I've had to punch all this into the browser again, which was a bit annoying. But that's only because I've moved from I did Monday's lecture on my laptop, and now I've moved to another machine. If I were to close this, I hope it doesn't make a liar out of me. Okay, then we go back into MIPS. So it's still there for us. So we've saved it to the computer. So when we open MIPS web again, it'll grab that cookie and load that program back in for us. Okay, so from here we can step through our code. Actually, first of all, so if we look at our program, decompile program, so this is what those assembly instructions have been turned into. So these are the addresses in the code segment where this program lives. This is what the machine instruction looks like. This is what the assembly for that machine instruction would be. Can everyone see that okay? And then this is what we actually had as our assembly. Okay, so you notice that these are a little bit different. So if you remember, we have this special register called 0. Okay, and this register always has the value 0. So if we want to load an immediate value, so load a constant value into a register, then that's the same as adding the register that has a value of 0 to some literal value and storing that into another register. So we don't actually need this load immediate instruction over here. We can repurpose another instruction to do that, but we still have the assembly code for that instruction. So that just makes it easier for us to read. So if we look at our best friend, the MIPS instruction set, where are you? LI is incredibly difficult to search for, so there we go. LI, so you can see in our MIPS documentation, it takes a register and an immediate value, but this is actually a pseudo instruction. So the pseudo instructions are instructions that are implemented as either one or more other machine instructions, and this assembly instruction just becomes a convenient way of representing that sequence. Okay, so over on the right here, we have a list of our registers. We don't need this just yet. But you see, we don't have any registers listed there yet. Okay, so that's because in this part of in MIPS web, it's only showing registers that have values in them, okay? Or valid values in them. The registers always exist and always have values, but it's only when we write to them that they become a defined value. Okay, so as we step through, so you'll notice MIPS web has highlighted this instruction for us, the ADDI or the LI, and you can see that we now have the number 3 in T0. If we step again, the next instruction, we're loading 5 into T1. In the next instruction, we are multiplying these two numbers together to get 15. And if we step again, we get an error here. Could not find instruction at 40000C. Okay, so 8 plus 4 is C, so that would be down here. So our program has just started executing the code that we, the CPU just takes one instruction at a time and executes it, right? So once it's executed this multiply, it grabs the next instruction and tries to execute it, but there's nothing there. So what we do in this case, and this is something I'm going to gloss over because we do cover it later on, but we have the code for returning, so effectively in your main function, this would be return 0. Okay, so now when we step through, there's our decompiled program, there we go. Okay, and then it returns from that main correctly and we don't get an error at the end there. It also means we can just run this program. Okay, and then it runs through. It's not so interesting because this code isn't communicating out with the real world yet. Okay, so has everyone got that in their MIPS web, this code? So what I'd like is for you to have at least this here. This skeleton code, the label main, and then the code here to return 0 from main. Has everyone got that? Has anyone got that? 1 thumbs up, 2 thumbs up, a hand. Yes, excellent. Okay, because now it's your turn to have a go. So I want you to have a little bit of practice with MIPS web. So a very simple program here. set T0 to 10, set T1 to 7, subtract T1 from T0, and store the result in T2, add 5 to T2, and so I need to add to that. So add 5 to T2 and store the result in T2 as well. And we haven't gone over subtract yet, but I'm sure that you'll be able to find subtract in the MIPS documentation and work out how that is used. So the discussion is still working. Store that in T2. Yeah. So that question was where to store the final result? So just store that back into T2. Yes.
What's the difference between like sub and sub-u and add I?
Oh, good question. So over here we have, what? Wrong one. Add and add I. So you can see in the way that these instructions, the arguments that these instructions take, for add, we have 3 registers. So this will take one register, add that to another register, and then store that back into the first register. And add I takes an immediate value, which is, it's like saying the value is immediately in the instruction. Okay, so that's the constant that you put at the end. Where are we? So that would be your literal there, or your immediate. And sorry, u. So add u. So this is for, we only use sub though, right? Yeah. Oh. It's unsigned. Do we ever use it though? It's always sub, right? So, okay, so when you're, so we go into this later in the course, so I don't want to get too bogged down into it, but for now we're not going to, so the difference is one is an unsigned operation and one is a signed operation, but we're going to keep using the signed operations for now, and we're going to be talking later on in the course why we might have different instructions there. All All right, so I assume that everyone has finished with that. So what answer did you get in your T2? Okay, I'll hack that up quickly and we'll see if we get the same answer. What was it? 10 and 7. Subtract T1 from T2. Okay, and then we have one final add. Whoop. It's an add immediate. So with the result in T2, we want to add 5. Okay, so 10 into T0, 7 into T1. Then we have 3 in, so then it's much better if I look at the decompiled window, isn't it? So then when we execute our subtraction, we end up with 3. 10 minus 7 is 3. Okay, and then we're adding 5 to that final result and storing the value back into T2. So we should all have 8 in our T2 register at the end of that program. Does that work for everyone? No? What did you have? Did your code look like this? Question over here, yes.
My code's like the same except for the addition one I was going to add T2.
Sorry?
Why do you have 2 T2s?
In the addition, why do I have 2 T2s? Okay, so we have to specify the register that we want to use, that we want to add to. We need to specify the value that we want to add to that register, and we need to specify where that result's going to go. Okay, and so it's very nice that these assembly instructions are laid out such that the first value is where the result gets stored, so it's almost like that register equals, and then the arguments as well are usually in the correct order for us. So you can see here this sub T2, T0, T1, I can say T2 equals T0, T1. Yes? Can these registers only store integers? Yes, and specifically only 32-bit integers. Yeah. Sorry, what was that?
I didn't put add I, I just wrote add.
You just wrote add. If you just use add. Oh, no, little shortcut. Okay, thanks for mentioning that. So if we, okay, so first of all, let's try, so you had just the add. I would have thought this would end up with the, so I still end up with 8 at the end there, but I do end up with a bit of a different instruction stream. It's taken the add, and you've given it a constant. So what it's actually injected in the machine code is the code to load 5 into a register so that it can use the add instruction, which takes registers rather than immediate values. So it's used this at register as a temporary. But perhaps you just needed to step through one more step in that code. Sorry? Okay. I think there was another question. Yes?
Instead of subs, can we do like add but with a negative in front of T1?
No, not with this format.
And can we add like more, instead of just T2 and 5, can we put like more numbers after 5?
Okay, so, sorry, I always forget to repeat the question. So the first question was, can we just add a negative here and turn this into an add? So the answer to that is no, because we're now performing an operation on this register, right? We would first need to multiply T1 by -1, and then we would be able to use add instead of sub. And sorry, the second question, can you keep chaining things onto the end of this? So I don't know, like this. So the instructions have a, I would say strict, but someone's just shown me a shortcut today. So they have a pretty strict format where you have just 2 registers. I think this will become clearer later on as well. I'm about to go through some lecture slides that will highlight why you can't do this. But yes, so each instruction, if you wanted to add multiple registers together, you would need an add instruction for each of those. And this first register, we would normally call the accumulator, which keeps accumulating the partial sum as we go. Are we going to have access to the instruction set? Yes, this whole page will be available to you, and it has a lot more in here other than the instruction set. But yes, we will definitely give you this, so please don't try and remember all the different instructions. And there was one more point. So I think I found this out by accident one time as well. So apparently we don't need to have that first value there. It's just if we have one register and then a number, it's assumed that the result is going to be in that register. So let's step through this just to be sure. We can just look at the... Okay, so we change this back to add I. Okay, so this is our return 0. Okay, so we can see that there we go. So the assembly that we typed in was add I, and then we just provided the T2 register and the number 5, and the machine code has actually turned that into the T2 equals T2 plus 5 for us. It's expanded that for us. Whoops. So it seems that it understands T2 plus equals 5 as well. Yes, these are decimal values, so hexadecimal, I forgot to highlight this, hexadecimal always has the OX in front of it, or usually has the OX in front of it. So we can use hexadecimal as well, but we need to put the OX in front. The output, in MIPS web, I believe it's always hex. Oh, actually, I think it's always decimal. Oh no, sorry, it is always hex. But I believe when you're using the MIPS command line, which I'll talk about later on in lectures to come, I'll show you how I can print the you can choose what kind of notation you want for the result, whether you want hex or decimal. Okay. I think that's it. Are we ready to move on? Are there any other questions? Okay, so I mentioned on Monday that we have 32 registers in MIPS. So these can all be referred to as, that's not quite the same. So we have the T1. I'm just trying to demonstrate this. So we have these symbolic names for our 32 registers, right? We have the 0 register. So that has the symbolic name of 0. And that just happens to be register number 0. So we could also put this into MIPSy like this, okay? So this lecture is being recorded, by the way. Okay, so our register numbers here. So this is in the MIPSy instructions as well, or the MIPSy guide. So again, you don't have to worry about remembering this. Okay, this is just actually a snapshot from that. So our 32 registers, they have symbolic names to them, and some of them have very special purposes, and others just have a purpose by convention. And we'll go over this a bit more later on in the course. But the main thing for you to think about, to remember here, is that for all your mathematical operations, for all your opcodes, for now you should just be sticking to T0 to T7. And we are just about to go into using V0 and A0. Okay, so we wrote a simple program that can do some simple maths, but that wasn't very exciting, right? So how do we do input and output? How do we interact with the real world? Because what is a program if it can't interact with anything else? Okay, so for that we use system calls. So none of the instructions that we have can interact directly with the outside world. Okay, so for example, printing to the terminal and scanning from the terminal. So instead we request that the operating system perform these tasks for us. And this process is called a system call. Okay, so the operating system can access privileged instructions, so they're instructions that we're not allowed to execute. And it also has more access to the system so that it can communicate with devices. So MIPSy will simulate a very basic operating system. So it has some very simple system calls. So real system calls will be explored later on in the second half of the course. Okay, so these are the basic system calls that MIPSy provides. So we have a printf, but we have a fixed format here, right? We just have a %d, so print an integer. Okay, and for this, we need to, right, so we need to, the first number here is the system call number. So when we want to make a system call, we load this system call number into the register V0. And some of these system calls accept an argument. And those arguments are to be put into the register A0. Okay, so for printf, we would put the number 1 into V0, and we would put the integer that we want to print into A0. Similarly for scanf, so for scanf, again, this takes a specific format string here. So %d would be for an integer. So we load the system call number 5 into V0. And for the argument, there's no argument here, but there is a return value. Okay, so once the system call completes, we expect the integer value that was read to be in V0. So we also have printf with a %c, which is the equivalent of putchar, and a scanf with a %c, which is a bit like getchar. Okay, so 8 and 12 we don't use much in COMP1521. So there are more advanced system calls as well. Okay, but some of these are not implemented by our MIPS OS. So this is these are like the documented system calls for an operating system, but only some of them have been implemented for the operating system that you'll be using. So other system calls will only be used for challenge exercises in 1521. So we mainly focus on that printf print int and get int. So let's print the number 42. So how might we print the number 42? Okay, so let's remove this. So to print the number 42, we need to load into A0 our argument, the number 42. We need to load into V0 our system call number. Oh, I've forgotten what that is though. Sorry?
I think it's 1. Yeah, it's 1.
Sorry, what is 1?
The number that's to be loaded into V0 to print.
Okay, thanks for that. So I've forgotten what the number is, so I go to my MIPS documentation, and we have a section here on system services. Okay, print int is indeed number 1. Okay, so I need to load into V0 the number 1. And then the instruction for issuing the system call is just called syscall. Okay, so this instruction will cause an interrupt in the processor, and then the operating system will handle that interrupt. It'll look at your register values and go, oh, you wanted this. Okay, I'll do this for you. And then when it's done, it will return control back to your MIPS program. Okay, so we're loading 42 into A, 1 into our syscall number into V0, and then down the bottom here, that's our I/O window. Just there. Okay, so we're printing out the number 42 here. Okay, so as you remember, I forgot what the system call number was for print int. So why don't we define that? Print int equals 1. That's all we have to do here. We don't need to do a hash define or anything like that. We just say this symbol should be equal to 1, and then we can say print int in here. Okay, and that also helps you when you're reading your code. So instead of seeing this magical number 1 going into V0 before you issue the syscall instruction, you see print int, so you don't have to look up and remember, oh, what was the system call here that I was trying to do? Okay, so the system call workflow. So we specify which system call we want in V0. So for example, print int is system call number 1. We specify the arguments, if there are any, in A0, and we transfer execution to the operating system using the syscall instruction. And some syscalls return a value, and this is all specified in the system call table here. Result. So none of these return a result, but all of these do. Okay, so assembly instructions, so an overview of the syntax, sorry, I'm going to try and run through this quickly. So assembly instructions, each on their own line, generally a one-to-one mapping from assembly to the binary machine code. However, assemblers also provide some pseudo instructions for convenience, and I learned another one today. So pseudo instructions turn into up to 1 to 3 real CPU instructions. For example, so you will see many more as you write your code in MIPS, many more examples of this. Okay, what do MIPS instructions look like? So we have a 32-bit instruction, we can only pack so much into that, right? And the CPU is an electronic circuit. Okay? It needs to decode these instructions and process these instructions as a circuit. So what we do is we have only 3 types of instructions, so that helps simplify the circuit. So for the first type, the R type, so this is a register, this is an instruction type that operates only on registers. Okay? And you see, regardless of, so the opcode here is what the instruction is, so it might be an add or a subtract, etc. So you can see here, it doesn't matter what the opcode is. In this machine code, all the registers are all put into the same part of this machine code so that the circuit is able to decode this instruction more efficiently. Okay, then we have the I type here. So I for, not for instruction, but for immediate. So with this, so these instructions in this format, they take an immediate value. So maybe it's a memory address or a constant as the last part of the machine code here. And the J type, I'm jumping a bit ahead here, but the J is for jump. Yes, I got a little chuckle. All right, so in this case, we only have 1 register and perhaps a really big constant. Okay, so the operation is in the opcode, and we have 0 or more operands, the things to do it over, which are the registers. So for an example, so what you're seeing here is the binary machine code and the assembly that would map to that, that binary machine code. And the different parts of that instruction, that assembly instruction, are color-coded to map to the different bits in the machine code that they represent. So the add-I here would be 001000 as the opcode, and R1 would be T0 here, R2 would be T1 here, and the memory address or the constant here is 12 here, and if you know binary, that's the representation in binary of the number 12. All right, hello, COMP1521. So no, so you can't say that you've written your first program until you have written a Hello World program, right? So why don't we get to that? Okay, so maybe we want to print a character. So that is system call 11. Print char equals 11. Print char, and we can put in here H. And as we step through, we've issued our system call, and we've printed the letter H. Whoops. Okay, so what do we do from there? We want to print an E, an L, an L, an O. So perhaps we can copy and paste and just say H, E, L. This is getting a bit tedious, right? So this is saying put char for every single character. So how would we write code that more looks like this? We've got a string here as an argument. We have a system call, print string, number 4. So how are we going to, so we have the system call for printing the string. But where do we get this string from? Where will this string here be stored? Yes? A0? Yes, so that's where the argument goes, but we can't pack a whole string into that argument, right? We can only put an address into there, yes?
Oh, yeah, store it in like a variable and then put in the address.
Yes, but we don't have variables in assembly. We only have registers. So yes, so in C, that would be, this would be, the type of this would be a character pointer, right? And that would be referring to an address in the, which segment? Sorry? Which segment of the program? So we have the text section and we have the data section. So something that has been implied in the programming that we've been doing is that all the code that we're writing, why is that red? I'll work it out later. So, no. I don't like seeing red. Oh, it's because of the question marks. Okay. So what's implied is that the code that we're writing is going into the text section or the code section. Okay. But we can make that very explicit by putting the compiler directive in there, the assembly directive .text, to say that this is the text section. So what do you think we would put if we want to create a data section? Data. Okay, so now we have our text section, we have our data section. And we want our string to be in this data section. So how do we put a string in the data section? So for that, we have another directive, ASCII, Z. Don't forget the Z. Better make sure I get this right. 2 exclamation marks. Ooh, can we see that in the data section already? Need to. There we go, we can see, so if we click on this third tab here, we've got our data segment there that we can examine to see what the contents of our data segment is. And just like the hex dump that I was using on Monday, we have address on the left, and then we have this sequence of bytes. Okay, so these are represented in hex. So sometimes we do chop off the OX in the front because it's just assumed that it's going to be hex. And over on the right, we have the, if that byte value represents a printable character, we'll print the character there. Otherwise, we'll just have a symbol for anything that we can't print. So that's handy for seeing if things are strings and what the value of those strings are. So we have this string in our data segment. So how do we refer to this? Yes, question? Well, it will be stored in the file when it's compiled, and then yes, it'll be loaded into RAM from that file. Okay, so one thing we could do, so it's been put into this program at this address. So over in our source, I'll step through. Okay. So we've now, so remember this system call for print string in A0, it expected a pointer to a string. So we've now given it a pointer to a string. We said, we put our string in the data segment. We worked out what address that was going to be put at. and then we gave it the memory address for the print string as the argument for the print string system call, and now we're able to print the string. But what happens if we add something else in here? So that's going to change our address here, right? Yes?
What about if we loaded the binary decimal representation of that same number?
Sorry?
Would it still get the string if we loaded the decimal version of OX1001, whatever?
Yes. So the binary and decimal values that literals that you put into your assembly, you can use them interchangeably. Programmer mode. Hex OX10010000. So that's our hex value. We can definitely put the decimal value in here. But you can see this value is a little bit not so easy to read. Doesn't like the commas either. What is it not liking here? Yeah. Well, we just need to run that. Okay, so that has worked as well, but the point I wanted to highlight here is that these hexadecimal numbers can be a lot more meaningful to look at than the binary equivalents. Okay, but you can use them interchangeably. But what we can do here, because we don't like having constants in general in our code, right? And we don't want to guess whether the assembler is putting our data. So just like we have this label for main, we can put a label for our string. And then we can put a label in here. Okay, and the assembler is going to map these together. It's going to say, oh, you're expecting a label somewhere in your program, and that label is representing a memory address. So I'm just going to put a placeholder here, and I'm going to fill in that address later on. And then as it gets through your code, it goes, oh, I found this label now, and it kind of backfills those addresses for you. And we're no longer loading an immediate really here, or a constant, we're loading an address. So we should really be using the LA instruction, load address. Okay, but as you will see, oh, it's done that for a different reason. All right. Okay, so if we're providing an address, we should use the LA, and if we're providing a constant, we should use LI. Sorry, if we're using just a decimal value, we should use LI. Okay, but in terms of the machine code, that ends up being translated to the same machine code. It's just for, like, as we're reading the assembly, we can better understand the assembly code that we're reading. Okay, so if we run this, so we've added the labels. We just need to run that, and we can see we are still printing out the hello world string, but we haven't had to have any hard-coded values. Okay. So I'm going to jump over this slide, but one thing I want to mention is we have ASCII and we have ASCII Z. So what is the most important thing that you need on the end of a string when you're programming? The null terminator, right? Because that's what we look for the end of the string. So that is what the ASCII Z is. The Z tells the assembler, put the null terminator on there. Otherwise, it won't have a null terminator. And if I added another string here after it, we'll print both strings because it runs over the end of that first one, which doesn't have a null terminator, and starts printing the second one. Okay, so in summary, so we need to, if we want to put strings in our data section, we need to add a data section. Then we pass the address of the string to the system call in A0. We need to use the .data directive to define the data segment. And then we use the ASCII Z directive to define the string. And we want to give that a label as well so we can refer to it in our code. Then we use LA to load that address into a register, and then we can make our system call. Ooh, of course, we need to put the system call number in V0. Plagiarism check. Hello string, hello message. A little bit different. Okay, so we have another example here. To translate into MIPS. So what I like to do is copy paste my C code. Okay, and now we just need to write assembly code that maps to that C code. So for so this is our main. Let's have a comment here. A is in T0, B is in T1, because most of the bugs that you'll have is probably using the wrong register for the wrong thing, and you will come to really appreciate having really good variable names for your C code once you finish this course. Okay, so enter a number. So that's a printf. So we need our data section. First prompt. Don't forget the Z, enter a number. Okay, so load address into A0. First prompt. Li into V0. Print string. Syscall. What happened to my return 0? Li to V0, 0. And that magic. Okay, let's just test this quickly. Enter a number. Okay, now we want to read a number in. So we have our prints. Now we want to read int. That's number 5. Okay, so in this case, we only have the system call. Sorry, we only have the system call number that we need to write. Okay, so the result is going to come back in V0. So let's go ahead and move into T0 the result that we just read in. Okay, and then we repeat the process for B. But of course, we're printing the second prompt. And we're moving that into T1. The average is, and then we have a %D, but we can't create a format string here. We can only print this string and then print an int and then print the rest of the string. Okay, and now we actually need to compute the value. So, oh, it's the average. So add, let's just put the result in T0. T1, ooh, I'll use the shortcut. No, I'll spell it out properly. Okay, so we add our two values together and then we need to divide by 2. How do we divide? What's the instruction for divide? There we go. Div. Okay, so how does this work? So we take R5, so we take 3 registers, we go RS divided by RT, and we put the result in RD. First we need the number 2, because this is expecting 3 registers. So let's just store the result in T0 again. So we want to do T0 and T3. Okay, so that's our, these 3 instructions is our A plus B, and then we're dividing by 2. But we still need to print the result, so maybe we can have a shortcut. We'll throw that straight into A0. We'll load into V0, print int, and then we will syscall. Okay. So refresh. No, doesn't want to let me. Yes. Why is dot data at the bottom? That's a good question. We could throw it at the top if we want. In fact, in most of the code you'll see it's at the top. It's just, I don't know, I like to put it at the bottom. That all looks fine to me. All right, not sure what happened then. I just refreshed the window and now everything's fine. Okay, so if we run this code, should we step through? I'll step through a little bit. Oh, decompile program. Okay, so that was our first system call. That prints the prompt, enter a number. Okay, and then down here we enter the number. 12. Whoops, 11. That'll do. Okay, and then we can keep stepping through. Then we have the prompt for the second number, and then the system call to read that second number. Let's go 5. And then as we step through, we print the result string. Then we calculate a plus b divided by 2, and the result will be in A0. 8, excellent, yes, because 11 plus 5 is 16, divided by 2 is 8. So we have the correct result. Number 8, we're printing the right value, and there's something I've forgotten, of course. Okay, the second most important thing to have at the end of your string sometimes. Okay, so we've had the average is, then the number, but we didn't print this new line. Okay, so we talked about putting, I did this before, but we talked about putting decimal values in here. We talked about putting hexadecimal values in here. Well, a character is just another way of representing a number. Careful with comments, they quickly get stale. Some people say, make the code that you write document itself, because if you have comments and code, the comments get out of date, and then you get confused about what's correct, the code or the comment. So always make sure our comments are up to date as well. Okay, so in order to test this, I did a lot of work just stepping through that program, right? What I can do in MIPS is set a, how do we do this again? Set a breakpoint, say at put chart. I can run into the number 11 again. Okay, and it stopped the program here for us. So now we can step through. Pass. What happened there? Question, yes?
Does the program automatically start in the text segment if you don't have dot text at the top? Before it hit the
Yes. So the program will actually, it'll actually look for the label main and start executing from main. So if you have code before main, that's fine. If it's after main, that's fine. But it'll actually look for the main to call to as the starting point for your program. Great point, okay. So now we can step through, and yes, we have that new line character there. That kind of wasn't very interesting right now because there's not really anything that comes after this. But trust me, you're going to forget that new line character, and your text is going to start just streaming along in one single line. All right, yes, question.
How do you enter the input in the MIPS like IO? Because I've been trying to enter it, but unlike your example, it's not working for some reason. I do the right syscall, it doesn't let me enter it like on the IO.
Okay, so if you run it, it should stop once you make that system call waiting for input, right?
Yeah.
And your box doesn't go green?
It does go green, I can't enter it in the black. Oh, wait, you enter it in the green line.
Yes.
Oh, my bad.
That's all right. Okay, so I want to repeat the question and the answer. So there was an issue with entering the number in here. So you don't enter it in where the black cursor is, which would seem completely reasonable, right? But no, you don't enter it where the black cursor is. There is a green box at the bottom here. That's where your input comes in. Okay? Another question, yes?
Why is there like an MLFO line on the D compiler? You scroll down.
Whereabouts, sorry? That's a very good question. Let's see, mflow. I've never noticed that before. CP move instructions. Okay, so there's some special purpose registers in the CPU. That's a really good question, by the way. So in the assembly code, where did this instruction come from? The mflow, and this is CPU move instructions. So this is taking the low register and moving it into one of the standard registers that we can use. Okay, so it's taking the special purpose low register and moving it into the general purpose ones where we can actually use it. And the reason for this is because actually, I can just search now. No? Div. Okay, as you can see here, the div instruction is actually doing the division, and the division itself, the result of the division goes into the low register. But hey, while we're here, we may as well take the modulo operation as well. So the remainder goes into the high register. But then we need to load from those special purpose registers into our general purpose registers so that we can use them. And the div instruction that I used, that's a pseudo instruction for those sequences of real machine instructions to do the div and to copy the special purpose register over. Okay. All right, let's move on. Let's skip over this. Okay, load immediate to LI to load a fixed value. We can use LI as well for fixed addresses, but we really prefer to use LA, load address. So that just tells us when we're reading the code back to that this value or label coming up is going to be used as an address. And move if we just want to move from one register into another register. Okay, so we have, as assembly language syntax recap, we have labels. So we just say what the label is and then we put a colon at the end of it. So these will represent memory addresses. So even main, that's a memory address in your code segment of where the CPU should execute when it wants to run the main function. And constants like defines, we can just write the text that we want for that define and equals and then the number. Okay, MIPS control, how are we doing? Okay. I completely forgot about the break. So can we power through and, yes?
When we declare like constant, we declare it off, but we have also like the data section.
The constant, do we...
I thought the data, like the constants go in the data section, so it's fine to put on top in a separate section.
A very good question. So we have constants which end up in the data section, and we have constants like hash defines. And they're a little bit different. So in our source code, for example, this print char, we don't really need that in our data section, right? This actually gets encoded into the machine code. So when we have, so this first one here, li v0 print string, so that constant is actually going to be baked into this machine code, right? So we don't actually need it in the data section. Okay, so yeah, two different kinds of constants. Okay, so far our programs only execute linearly. Yes, question?
What are the constants?
Sorry?
Do you need constants only store integers? Because when I put in string in there, it got really mad at me.
Oh, really?
Yeah, like for the hello comp thing, if I put hello comp in the variable at the very top, it got angry.
To be honest, I haven't tried that before. Failed to pass? Yeah, I guess it's only the integers.
Or do you
Actually, come to think about it, it doesn't seem very useful to have a constant that is a string, because you're effectively doing the same thing right down the bottom in the data section, right? You have a label to the string. Yes?
So do these constants basically act like registers when 32-bit values can go in?
Sorry?
The constants we apply at the very top, are those only 32 bits?
They're just to be used, so it depends on where they're used, right? So it's, yeah, depends on where they're used. So I can't think of a way that a way in which it would work to have those constants to be defined as more than 32 bits, but there could possibly be a way. Okay, so far our programs only execute linearly, so one instruction after the other. How can we conditionally execute code? How can we loop over code? Because code is not very fun unless you can jump around and repeat stuff. Otherwise, you just have to copy and paste all your code. Okay, so for that we have branch instructions. We have conditional branch instructions, and they have the form if, and then some condition is true, then jump to some offset. So in terms of offset, that takes a program counter, the PC, and it's just going to add this offset to the program counter if the condition is true. You can imagine in an electronic circuit, that's quite a simple thing to do. If some condition is true, add something together. Okay, we also have unconditional branches. So this is, we just have the letter J, and then we can just provide some address. Yeah, the most important difference between these two is that the branch instructions, they're normally used for just smaller jumps, whereas the J, if we need to make a larger jump to like maybe very far away in our program, then we use the J. But we'll typically be using the branch instructions. Okay, but offset and address. So thankfully, offset and address, just like our string, we can provide those with labels instead, and the assembler will work out the offset based on where that instruction, where this branch instruction is, and where it's expected to be branching to. Because otherwise, if we added code or removed code, we'd have to be constantly going through and changing these offsets. Simplified C. Okay, translating C code directly to MIPS is challenging. So we're going to get to the branch instructions in just a minute. But yeah, translating your C code directly into MIPS is challenging. So the recommended process here is to first simplify your C code. Okay, once your C code has been simplified, then we translate it into something we call simplified C. So this means that each line of your simplified C code is going to map one-to-one to a MIPS instruction. From that point, You can compile your simplified C, you can test it, and you can make sure it works, and it's, yeah. So at that stage, you can make sure that your translation to simplified C is correct. And then you translate each line of simplified C to MIPS. Okay, there's a little trick that we need to learn before we can do this, though, in practice. So in C, the go-to, I want to say instruction all the time now, the go-to, and I want to say directive. What is it in C? My headspace is too much assembly at the moment. The go-to keyword allows jumping to any arbitrary label within a program. A label in C code? Yes. Okay. We have labels in C code as well, and the go-to allows us to jump to those. So this means we can effectively jump around our program however we wish, and when we do that, it is impossible for anyone reading the code to work out where you could possibly be going. Okay, so what will this code do? Sorry? It's an infinite loop. Was that easy for you to see? So we have main, we go to sleep. So we jump over the please pay close attention. We go to sleep instead, and then we say you are getting sleepy, and then we jump back to sleep, and then we are in an infinite loop saying you are getting sleepy. Okay, so I've been over these lecture notes quite a few times, right? And even I still look at it and I go, okay, what's the control flow here? There's no structure to this code. We have go-tos. What is going on? Okay, so with great power comes great responsibility. So our favorite programmer, Dijkstra, all the way back in 1968, he was already saying, don't use go-to. Go-to is considered harmful. So don't abuse go-to. Don't use it in your actual C programs. So go-to makes programs much more difficult to read, makes it hard for the compilers to optimize it as well. And in general, do not use go-to without good reason. So we will use it in this course only for writing the simplified C to translate into MIPS. Okay, so I'm going to go through some examples of simplifying your C code. Okay, so this is C code here. We have, okay, so it's mainly this if statement that we're simplifying here. So we have this complicated operation here, the n modulo 2. So one simplification that we're going to do here is we're going to store that result into a temporary register over here. I can't highlight stuff. I want to highlight stuff. We're storing that into a temporary register, and then our if is now dependent on what that, I'm saying register as well, temporary variable. My head's too much in the MIPS, sorry. So we're storing the n modulo 2 in a temporary variable, and then our if becomes a test of the value of that temporary variable and some constant. Okay? But what might be, well, what should be completely new to you is we've gotten rid of our curly brackets. Okay, and instead we're using this go-to statement. Statement's the word I was looking for. So the go-to statement is going to, in this case, go to if even end. Okay. So what you'll see here is we've reversed our condition as well. Instead of checking whether it's equal and then executing the code, we're checking if it's not equal, and we're jumping over the code. Okay, and if it is equal, well then we execute the code, and then we can just keep going. Okay, so you might say, yeah, okay, this is not really that simple. It was a bit simpler before, but in terms of translating this to MIPS, this is going to make your life a lot easier. I did have a demo flag there for MIPS. Okay, I might shortcut this one though. We can leave our data section there. I got rid of my return again. Li v01. Okay, so we just went over printing a prompt and reading a number, so let's skip that step. We did division, and we also got to look at how to take the modulo. Okay, so how do we write this code? So let's assume the result in here is 42. Oh, it's modulo 2, so that would just be 1, 0 or 1, wouldn't it? So let's just assume that this is 1. We can keep this label. Return 0. Oh. So we keep this label. Okay. To do. Okay, I'm not going to spend time on that right now. Okay, so how do we convert this? If temp is not equal to 0, go to if end. Well, we have in this case, it is a branch not equal. Okay. T0, 0, and then we just provide the label. Okay, and then we leave the C code there as a comment to remind us of where this came from. Okay, so that's all we have to do there. So the complete list is, I'm going to zoom out, the complete list is in your favorite document, the MIPS documentation. We have branch equals 0, branch not equal 0, greater than or equal, greater than. We have a whole collection of these conditional branch instructions that will perform differently depending on the arguments that you give. Yes?
What does the PC plus equal set 16 do?
Where is that, sorry?
In the branch instructions, it says under like the PAE that we use.
This one?
Yeah, it says once the condition's met, then we go do that.
Yeah, so if the condition is met, then the PC, that's our program counter, right? So what we want to do with our program counter, so normally for our program counter, we would just be adding 4 each time, okay? But we want to change our program counter so it's jumping over some instructions, right? So we need to add to that program counter so that we need to add to that program counter more than the number 4 so that it jumps over the instructions in the true case. Okay, so we take our program counter, we add the provided offset, and in our case, well, in every case, instead of a decimal or hexadecimal value for the offset, we provide a label, and we let the assembler map them together. Yes?
Why do we have to bit shift it by 2?
Why do we have to bit shift it by 2? Okay, so we will go into this more later on, but the idea is we have these machine instructions. We have very limited bits that we can put in there, and our instructions are always 4 bytes wide, so the program counter should always have a value that's aligned to 4 bytes. So we don't actually have to store our offset in terms of the number of bytes. We store our offset as the number of instructions, and then we multiply the number of instructions by 4. So this less than is a bit shift, and the left shift by 2 is the equivalent of multiplying by 4. Okay, so then, yes, so in the instruction itself, we only need to store the offset in terms of the number of instructions, but when it comes to executing that branch statement, we add 4 times the number of instructions to get the memory offset. All right.
Could you replace the label with just the address of the offset?
I'm getting, okay, so the question is, can I replace this label with the address? I'm getting a little bit worried about the code that we might be seeing for the assignment. You definitely could, but please don't. So the problem with that is, like right now it's constant. Right now, my label is on line 24. If I were to add another instruction in here, li something, another instruction li, okay, so suddenly my label is on line 26, and now I have to go back through and modify all the constants that I had pointing to that line 24 to adjust it to be, you know, what the address of this label has changed. So let the assembler keep track of the address of the labels and where those addresses need to be used. Please use labels instead of decimal values. Yes?
So in that case, the dot license address would increase by 8 as you added 2 sets of instructions?
Yes. Yes? No, I can't explain the bit shifting again. We have a whole lecture on that. If you come up to me after the lecture, actually, I can explain it to you if you like. Okay. Okay, so I seem to have fallen behind time again. So we need to finish the lecture 5 minutes before 11. So I'm going to wrap it up there, but these slides have been published. There's a few more examples here of how you can translate the if statements, but I will be going over these in the next lecture. So thank you very much. I will see you on Monday. So where are we? Falling so behind this time. How am I falling so behind this time? Sorry? Yeah, true, I was already 20 minutes behind. And interesting ones as well.
What the shift was in the branch instruction until I finished computer architecture.
But you did the shifting in 1521, right? You just didn't understand why it was applied to...
Just call the branch instruction. You didn't actually do the shift.
Yep. Right, bit shifting.
Yeah, left by 2.
Yes. So we have, you know binary?
Yep. Relatively.
Binary. So the value here will be 2 and 0. So we have 1, 2, 2, 2, 3. Okay, so we have a value like this. So this left shift is basically saying these are and these just kind of fall away. Okay, and these will be filled with zeros.
Why we bit shift by 2 for the instructions thing.
Okay, so if we're bit shifting by 2, we're multiplying by 4.
And instructions have to align by the 4 plus x stuff.
Each instruction is 32 bits wide,
Yeah.
which means 4 bytes.
Yeah.
So
Try to in offset to a byte shift, and then you can just jump that many bits.
gave it something like 2 and know to go, what, times 4, 8. 8 down to the next one.
Yes, that's right. But yeah, we will be covering this more in depth later in the course. I mean, we have a whole topic on bitwise operations, which would be left shift, right shift,
Yeah.
bitwise and, bitwise ors, bitwise knots. So yeah, sorry, that's why I didn't want to
Yeah.
go through that. Didn't want to spend too much time on that, especially since I was running out of time. All right, you're welcome.